So let's look at a specific example of how to use a model for reconstructed past climate. What better thing to look at than the marine isotope stages that we are going to talk about for this period, 130,000 years. So here is how they are described. This is just from Wikipedia. So this is going back to more than 100,000 years and looking at 8 marine isotopic stages. Obviously, as we said, as glaciation and deglaciation happens, chemical signatures are left behind, so it identifies glacial, interglacial and stages, and you can see that the last glacial ice age that started here 135,000 years ago ended around 21,000 years ago. It reached its peak, and then it started to melt away, and we got into the Holocene. And you can see within that you have these higher frequency variations, which are identified here as 5, 4, 3, 2, 1. So those are the marine isotope stages. So we look at these 6. Basically, humans arrived, Homo sapiens arrived somewhere here 200,000 years ago, and this was a glacial, and then there was a rapid interglacial, and then we got into another glacial, right? So looking at this in terms of simulations from UVic ESCM, University of Victoria Earth System Climate Model, Common Model, whatever the acronym stands for. It's basically an intermediate Earth system model in terms of the complexity, grid size, and a number of components and so on. And it is run typically at a very coarse resolution. You can see that common horizontal resolution is 3.6 degrees in longitude and 1.8 degrees in latitude. You can imagine that means that orographic features like the Himalayas, Andes, the Rockies and so on are going to be very coarsely represented. Coastlines are going to be very coarsely represented. Processes being resolved are very coarse. 3.6 degree longitude is 360 kilometers, 1.8 degree latitude, depending on what latitude you are in, is almost 200 kilometers. So it's very close, but it does energy exchange, water exchange, and carbon. So this is important that it does carbon cycle in some ways, and has a sea ice model. So it has an atmospheric component, ocean general circulation component, marine ecosystems, chemistry, sediment model, land surface model, has a permafrost component and represents vegetation, not necessarily as a competition of multiple functional types of vegetation, but changes in vegetation types can be simulated. So here are the cycles represented: nitrogen, phosphorus, oxygen, organic carbon cycling, inorganic carbon, and so on. So does hydrology and runoff, etc., etc. This model is used to just validate itself. So here we are looking at global mean temperatures with the Hadkrut data that we had just looked at, and a scenario of older IPCC from 2007 or so, and you can see that given the atmospheric CO2 concentration changes over the industrial revolution period into the 21st century, the model is able to represent the variations in global mean temperatures. This detail here we haven't talked about. The observed temperatures have lots of ups and downs because of El Niños and things like that, Atlantic multi-decadal oscillation and so on, whereas models do not necessarily simulate year by year the same events, because they are just they have their own El Niños. Given the top of the atmosphere radiation forcing, models they do their own El Niño, La Niña, Pacific Decadal Oscillation, monsoons, and so on. But it's not a prediction, so the years of El Nino in the model do not necessarily correspond to years of El Nino in observation. For example, 97, 98 was a strong El Nino in the real world, but the model doesn't necessarily do an El Nino at the same time. So overall, what you look for is the low frequency trends given the anthropogenic forcing in terms of greenhouse gases, and of course they also include aerosols and solar variability and volcanoes and so on and so forth. The model gets validated against warmings. Polar amplification is rapid warming in high latitudes, a polar Arctic Circle, where ice albedo feedbacks and water vapor feedbacks produce much higher warming. So you can see that the model has significant differences in temperatures at the surface, but does the structure with latitude fairly well. So this is something that has to be looked at in terms of tropical warming versus high latitude warming. In general, it's doing higher warming at high latitudes, and it does global carbon budget compared to what we had looked at already in terms of fossil fuel emissions that are prescribed, land use change that is modeled, land sink, ocean sink, what collects in the atmosphere, and so on, and compared to some global carbon project data for 2018, for example, in each component. The important thing on the time scales we are talking about marine isotope stages is, of course, the so-called meridional overturning circulation. It is using the carbon-14, which is an age tracer. So just like oxygen has multiple isotopes, carbon has C12, C13, and C14. C14 is produced by bombardment of nitrogen by cosmic rays. So one of the protons gets converted to a neutron. So nitrogen is 7 plus 7, it becomes 6 plus 8, so 6 protons is a carbon, so it goes from nitrogen to carbon, but it's a C14, which is radio active, so it's unstable, and once it's taken up into trees for photosynthesis or into the ocean, it begins to decay. We know its half-life, and we can infer the age of the models. So here we are looking at a meridional section of the overturning or age tracers where there is deep water forming. See, the carbon-14 is taken from the surface and it sinks, and as it goes along older waters here, so you can see the Atlantic from the model, from the Pacific at various sections, and in the Indian Ocean and the global ocean, basically to confirm that the model has reasonable simulation of the ocean circulation. So this is what we are trying to capture. Basically, if we go back about 100,000 years, we have the isotopic signatures in delta O18. Remember that this is what remains in the ocean and corresponds to cold climates. So depending on how much excess O18 there is, you can infer cold and warm stages in the climate system. So this nice figure has shown all the millennial timescale oscillations, glacial, interglacials, and has marked major episodes of migration. So first migration of fully modern humans out of Africa here. Aborigines arrive in Australia. Migrations of fully modern humans from South Asia to Europe, from South Asia to Europe. So remember, we said somehow modern humans appear much later in Europe compared to South Asia. So whether there was migration out of Africa into Asia and back, and then from Asia into Europe, can be inferred from molecular clock techniques, mitochondrial DNA, and so on, that we haplogroups and so on that we looked at, right? So beginning of the agriculture and the great European civilization, Greeks, Romans, and so on. So if you expand this, you will have details of the mid-Holocene climatic optimum, medieval warming when the the Vikings colonized Greenland and Little Ice Age and so on and so forth. This is what you want to simulate. So here, looking at the simulation from UVic, global average surface air temperature simulation results from a 122,000 year time series climate simulation performed on the UVic ESCM and the MIS6, the marine isotope stage 6 equilibrium simulation result, 9 degrees C change there. Marine isotope stages MIS5E through 1 are indicated by broken vertical lines. So we're going time this way now. So marine isotope stages, and these are the various 5E to 5A, 4, 3, 2, 1 here, starting at 6, that's down here. Okay, so you look at this, you compare to proxy reconstructed data, and you try to make sure that the model is able to capture the glacial, interglacial, stadial, interstadial variations in this time period. This is a very long simulation for a model. If you do it with a full Earth system model or a climate model, it would take forever. That's why UVic, which is a simpler model with coarser resolution, is used, because the processes you are trying to capture are not necessarily needed at the details of a weather prediction or a climate prediction. So this is the maximum meridional overturning stream function simulation results from the same simulation and MIS. So that's what we said before. Hendrick Events H9 through H1, different timescale event here, and the Younger Dryas, which is here, are indicated with broken vertical lines. Hendrick events are basically where there is drifting glaciers coming into the North Atlantic, where deep water formation happens, and they affect the deep water formation, and those signatures are recorded in marine isotopes as well, in addition to the ones we saw here in terms of glaciations in stadial interstadials. And Younger Dryas was the hiccup that happened during the last deglaciation. Last glacial maximum was reached around 21,000 years ago. Deglaciation started, and around 11 to 12,000 years ago, the glacial meltwater that was sitting behind an ice dam in Lake Agassiz presumably got suddenly released onto the North Atlantic. A lot of fresh water would make it harder for deep water to form, because deep water forms by increasing salinity through evaporation, which is caused by warm water coming in with high salinity and warmer atmosphere holding more water vapor, so favoring evaporation. But if you release a lot of fresh water suddenly onto that region, then you cannot form heavy water anymore, because salinity gets reduced by a lot. So that led to a temporary refreezing, and Younger Dryas refers to a flower Dryas which reappeared during that time. There is an older Dryas, of course, which is why this is called Younger Dryas. So Younger Dryas is a good example of a very abrupt climate change which happened in just few years, and this is of great interest because in global warming we are constantly worrying about how quickly things can change. For example, if suddenly some ice sheet collapsed from Antarctica or from Greenland, what kind of damage could it do in terms of changes in meridional overturning, sea level rise, precipitation changes, and so on and so forth. So we'll come back and look at further details about how climate has changed over these marine isotope 6 till the end of the last glacial, to put a better context on climate impact on human evolution, which is of course our main focus in this course. Okay, so this gives you hopefully a good sense of how models are used to understand the processes in more detail than can be captured in just the paleo proxies. Of course, these models are also used for the future, as we said. Okay, let me stop it here.